Hello, everybody. Hello. Welcome to another day. So I gave you a lot of I talked a lot yesterday and gave you a lot of questions. So and it's clear talking to people that I'm not the only one who finds probability quite difficult. I don't know, how did you find these quite tricky? Yeah, fine. That's completely fine. I find these ones very difficult indeed. I have to sort of sit carefully, usually because there's 2 or 3 different ways of doing it, different ways of approaching the problem, which is nice, but is quite difficult. So I deliberately put the solutions up on the website, and I'm deliberately going to take some time to go through them this morning, rather than racing on to the next bit. I don't want to take too long, but just to take a bit of time to look at the sort of style of trying to solve these. So they're written up there, you can see, and they're on the thing, but I'll go through them on the board. So this first one was just flipping a coin 4 times and looking at how many heads comes up. And I guess my intention was to think of this as this idea of a probability tree, that the first flip goes heads or tails, and then we do another one, second one, heads or tails, and a third one, heads or tails, and the fourth one, heads or tails. And then if we complete this in a rather boring way, hang on, we're going to, yeah, we're tails, heads, tails, that's done. How many of those? Yeah, there's 8 there, and then we got another 8 down here, and then we go on and on and on and on, and we end up with how many branches? 16, yeah, 2 to the 4th equals 16 possibilities. We could also write these out. If you don't like these diagrams, you could write head, 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 and head, 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 tail, etc. And you end up with 16 of these. And the simple way then is just, if we assume these are equally likely, which they are, so there's a 1/16th chance of each of these, we can just count the number that have just got 1 or 3 heads. And it turns out then that what the events we're interested in are ones like this: head, 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 tail, and then head, tail, 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 etc. So we could write these out. We might be interested in head, tail, 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 and tail, head, tail, tail, etc. It's a bit boring, and we end up that there's 8 with 1 or 3 heads. So the total probability, we can just say, is 8 over 16 is a half. Now, there will be quicker ways to do it, which we'll talk a bit about today, about looking at combinations and things like that. But this was just by pure enumeration, about counting them. So that's the first idea. But we're using a lot of ideas here. We're using the idea of multiplying down the tree. These are independent events. The probabilities stay the same. So it's a half times a half times a half times a half for any particular path, for any particular branch, and then adding over the probabilities for the branches that correspond to the event we're interested in. Okay, is that okay? Okay, now the next one, these socks, these stupid socks. Honestly, who cares about these socks? Anyway, but now all we're interested in is socks. So socks are important. So we got this drawer, and we get up in the morning. So our drawer, here's our drawer, and it's got 3 white socks, these are socks, and 3 black socks sitting there. And we get up in the morning and we're sort of half asleep, and we just stick our hands in the drawer and we pull out a sock, and then we pull out another one. Now, notice I'm pulling them out one at a time, rather than pulling out two. Now, the problem is asked as if you pull out two at once. But it's exactly the same problem to think of pulling them out one at a time, and it becomes hugely easier by pulling them out one at a time. But you can do it directly just by pulling out two at a time, using actually a thing called a hypergeometric distribution, but actually much easier to think of them one at a time. So this is one of these areas where to solve a problem, you just change it slightly into another problem, and suddenly it becomes quite straightforward. Because now, if we think of it one at a time, the first one, there's 6 socks, so the probability of choosing a white sock is a half. So it's 3 out of 6 each time. But now, if we do choose a white sock, that's gone. Now we've only got 5 socks, so the chance of choosing a white sock now is 2 over 5, yeah. 3 over 5 are black. Choosing a white here is now, hang on, you've got 5 socks. You've taken a black, yeah, so it's 3 over 5, 3 white socks out of 5, and 2 out of, isn't it ridiculous? Here we are, mathematicians, studying socks out of a drawer, but very important. Then, so these are the, now when we work out the probability for the joint event, is white, white, we got white, black, we got black, white, and black, black. To work out these probabilities, we multiply down the tree. These are not independent events now. These probabilities change. But when we multiply down, we get 2 over 10 for that, 3 out of 10 for that, 3 out of 10 for that, and 2 out of 10 for that. Now, so we're using all the rules of probability here. Now we're interested in the probability of a non-matching pair when they're different. So that's those two. We add them up. Remember, we multiply down a tree, we add over the branches, and we get 6 out of 10. The chance of picking 2 different socks. Again, there, as I said, there's different ways of doing this. Now, the third problem is, what if we pick out a sock and we just put it back again? Now, we're really sleepy at this point. I mean, we really can't be able to pick it up and just put it back again and then take out another one. You still only have one sock. I mean, what's the use of that? But in those situations, these are independent events, and so all these probabilities just stay the same. If you put the white sock back again, this stays as a half now. And this is a half. Now this is actually an easier problem in a way, because it's almost like flipping a coin. And then these become, what are each of these? Yeah, they're just a quarter and a quarter. In fact, they're all a quarter, aren't they? Yeah, they're just like flipping a coin. And then we get a half. So you're more likely to get a pair when you don't put them back. No, you're more likely, you're less likely to get a pair when you don't put them back. Yeah, okay. Right, goodness me. Okay, so that's socks. So that's that one. Okay, now this next one, the double 6. Did people manage this one, throwing the 2 dice 24 times? Did people see how to do this? Yeah? Did anyone get an answer? I think, have I written the answer down? No, it's down here. But yeah, what was the answer? 0.491, yeah, yes, that's it, yeah, brilliant. Okay, so that's very good. Remember we had 1 dice 4 times was 0.52, so it's slightly in the man's favor. And this is 2 dice, 24 times. But the principle is exactly the same. I'll just wind this up a bit so you can read it, because this is the more formal argument. Yeah. So again, we do it like the other one. We consider getting a 6 and getting not 6. All right, that's 6 complement. So that's equal to 1, 2, 3, 4, 5. Everything other than a 6. And the first throw is, there's a 6 there. No, oh sorry, I've got this wrong again. This is a double 6. And I'll write that as 6, 6. So throwing that, and the chance of getting a double 6 is what? 1 over 36, yeah. So you throw 2 dice, the chance of getting a double 6, 1 over 36, which Cardano worked out in 1570 or whatever. So this, the chance of not getting a double 6 is 35 over 36. Now, we use the trick. What we want is the chance of at least 1 double 6. And we use the trick that the probability of at least 1, 6, 6 equals 1 minus the probability of no 6 sixes. Because this is an easier event to calculate the probability of. Because it's the event that we don't get, it's this on the first throw, we don't get a double 6, and on the second throw, and on the third, and on the fourth, and on the fifth. 24 times, which I won't draw in. So this is 24 times. All these events have to happen. So this is the only thing we're interested in. In all of these other events, vast number of other events, we're okay. It's just in that one. And the probability of this one happening is 35 over 36, because they're independent. So it's just 35 over 36 to the power, what? 224. And so what we want is 1 minus that. Now this is quite a small number. Actually, we can write that. We'll do some 1 minus 1 over 36 to the power 24. Now, these sorts of things, 1 minus a small number to a power, we start thinking about exponential approximations and things like that. We'll come on to that later. We'll do this exactly for the moment. But we can do some quite good approximations to these numbers. And when we do this, it works out at, what does it work out? 0.491. Now, it's funny, so some people thought, and which is a natural thing to think, is maybe the probability is just 24 over 36. Because there's a 1 out of 36 the first time. You're doing it 24 times, so maybe the probability is just 24 over 36. Well, it's not. It's, this would be a good approximation. If this was a tiny number, see, it's a bit big. And if this was a very small number, this actually would be quite a good approximation to that. And we could work that out by, this is, yeah, okay. That's using the approximation. If I did 1 minus, if I just used the binomial thing there, I would get that. 1 minus 24 over 36 is approximately 24 over 36. So that I would be using that approximation. You know, 1 minus the binomial theorem, what does it say? It says 1 minus x is approximately, to the n, is approximately nx. But that only works when x is really small. And in this case, it's a bit compared with n. And in this case, it's not very small compared with n. So this is a bad approximation in this situation. But it can be quite a good approximation. So you see what you're doing. So your intuition wasn't bad if you use that, but it's not good in these situations. The point is that this number could get bigger than 1. And so that would be a silly probability. Now, the next one was the writing the programs. Now, Emma wrote this program. I don't know how, did anyone get on and, did anyone manage this? I mean, I'm just, did people manage it? I put the code up here, and it's on the web. So, because what I'd like you to do is just try this, because this is also practicing using SciPy, very valuable. I've got to learn it myself. I'm trying to learn it. I did my first little code this morning, so I'm very proud of myself. So, so you've got to help me on this. But basically, the code says, Emma wrote this, but I won't pretend I wrote it. Oopsie. Oh, I didn't want to do that. Let's go back to, yeah, that. Okay, I won't go through this in great detail because you can do this yourself, but you've got to import some functions, and then this is just using NumPy rather than SciPy. You want to say how many times you want to do the experiment, how many times you want to throw the dice. Remember, this is throwing a dice 4 times. And this is initializing, because you're counting how many times a 6 occurs, and then you want to loop around 1,000 times, so as if you're throwing the die, you're throwing a dice 4 times, and then repeating that 1,000 times. You count the number of the results. This is, what's this doing? Calculating, any is 4 out of the throw. This is the number of, setting this to zeros, 0, that's it. Saying you've got 0 in each of the events. And then you throw the dice 4 times. There is a quicker way, we'll see a quicker way to do this. You throw the dice and use this function random, which just chooses one number from 1 to 6. So that function is essentially throwing the dice. It's quite neat. So it's just a mathematical. And then you get the throw. You say that's the throw, 1, 2, which could be anything between 1 and 6. So you might get, so you get 4 numbers there. Say 1, 3, 4, 2, or something like that. And then you check if any of them are equal to 6. And if they are, you say the number of 6s is added to 1. I'm sure there's lots of ways to program this. But you can, I think you get the feeling. And then the total probability of getting a 6, you add up. You've added this. This is now anywhere between 1 and 0 and 1,000. You divide it by 1,000, and you get this probability. And it turns out, in about half the sequences, you get a 6, and about half you don't. And that's the correct number, and you run that, and you get the answer. But and it should be close. After 1,000 times, it's starting to get close to the real answer. Now the SciPy one, just to show this can be a bit neater using a different function, this has got a function randin, which allows you to do the 4 throws from a single function. Rather than having to do that loop around throwing the dice 4 times, this will choose 4 numbers. Now this time, I mean, it's really odd. Apparently it has to go to 7 there instead of 6, which seems really bad that there's a change in the syntax between NumPy and SciPy. However, nothing to do with me. So that's what you can do in things. So I think you can see you can get these down to some quite terse code. And this one, this is even more complicated. I'll put these functions up on the site so you can have a look at them yourself. This looks at number of pairs of sixes. Throws 2 dice, and this is a way of throwing 2 dice 24 times. That looks a bit complicated. I don't think you should be too. I hadn't realized it was going to be quite so intricate. But if you want to study that, that's great. But I'm not expecting that to be reproduced. Okay, so that's how to do that. And this one. Yeah, the women, the college women. Anyway, we're going to do more of this kind of example later in the week on Bayesian analysis. And what it just says, it's just one of these examples of looking at a problem 2 different ways. So the way we look at this problem, first of all, is to say that 100 random students, these are men and women, there's 70 men and 30 women, and 28 smoke. Of the men, you've got smokers and not smokers, and the women got smokers and not smokers, and 28 of the men smoke and 42 don't smoke, and 30 women, of whom 18 smoke and 12. So this is a very interesting country. This has got a slightly odd culture that might not match your own, but actually Scandinavia is a bit like this. You go to Denmark and all the women are smoking. It's extraordinary. Anyway, so this is Denmark. This is Denmark here. Denmark. Yeah. Okay. So how can we could construct this as a 2-way table, which is quite a useful way to think about it, as male and female, smoker, non-smoker, and we got 70 males, of whom 28 smoke and 42 don't, and we got 30 females, of whom 18 smoke and 12 don't. So the way to think about this now is that we built the table this way round, but we're actually going to analyze the table this way round. We're now going to say, if I find a smoker, in other words, somebody down here, what's the chance they're a woman? So it's like there's 46 of the people have ended up down here. What's the chance they're a woman? Well, there's 18 out of the 46. So the answer would be 18 out of 46. So yeah, we're going to do a lot of this sort of reasoning later on in the week. It's called Bayesian reasoning. It's when you reverse the conditioning. You construct the table one way, and it's a matter, these are odd problems. They're induction problems because you're trying to work out what gave rise to what I saw. And as we'll see, there's a whole theory of statistical inference that uses these ideas. And the final one's a really nasty one. This is an open question. I'll allow anybody to do anything. The final one says, it's back to the socks again. Back to the socks. You've got, but this time we don't know how many socks there are in the drawer. Let's say there's W white socks and B black socks. All I know is that the probability, if I take out 2 socks, the probability that they're both white is a half. Now, the probability the first one is white, again I'm going to do what I'm interested in this. I know that that probability is a half. Now the probability the first one is right is W over W plus B. Now, it's without replacement. So what's the probability that the second one is right? Yeah, W minus 1 divided by WB minus 1. Exactly. So we've got an equation that W over W plus B times W minus 1 over W plus B plus 1 equals a half. Oh, minus 1. Sorry, thank you. Just making sure you're awake. Obviously my deliberate mistake. So the thing is just to solve that for integer values. And that is not straightforward. I mean, I'm not a number theorist, but you know, this is all theory of Diophantine equations, trying to solve polynomials with integer values. Because I can rearrange that to get 2 twice W, oh dear, W minus 1 is W plus B all squared minus W plus B, and rearrange all this into a quadratic, either in W or B, and or both, essentially, and I want integer values for that. Now, it turns out, did anyone find any solutions? It's trial and error, really. Yeah, I mean, that's the only way I can think of doing it is just to search. Because when you put B equals 1 into here, if we put B equals 1 in here, we get a nice 2W W minus 1 is W plus 1 all squared minus W plus 1. And when we solve that, it actually all cancels out, and we get W equals 3. So there's one, if you just have 3 white and 1 black, the chance of 2 whites is a half. Did anyone find any other answers? Oh, what? 15 and 6. Does that work? Okay, so 85 and 35. Okay, so they're always in about the same fraction, but to get an exact integer value. Well done. Okay, so I don't know how to do an algebraic solution to that, but well done. Great. I'm going to go through now some new stuff. This is all on the computer. We're going to move into a slightly more formal way of thinking. So we're going to cover some of the material again, but slightly more formally. So we've already seen this, as we've been doing this already, that if we got an experiment with n possible outcomes judged equally likely, then for a set with cardinality R, if we count the number of elements in a set A, the probability of A is just the way that satisfied A divided by the total number of possibilities, R over n. So working out probabilities become a problem of enumeration. And that's what we've been doing so far. We just count the possibilities. So the idea of the next bit is about how to do that counting in more complex situations. So the first way of counting is, the first situation that we meet is when we've got, we're doing sampling with replacement from a set of n things. So we do essentially R samples of n things. So we could just say, okay, if we're taking R samples, so we could just do, we're doing 1, 2, up to R, and the first one can be any of n things, and the second one can be any of n things, etc., etc. So we end up at the end of this with n to the R possible outcomes. So that's the simplest situation. So it's like, you know, you're taking a ball and putting it back. Exactly the same number of branches at each situation. These are ordered sequences, there's n to the R. Okay, The next interesting one is when we don't put the ball back. And so after we've sampled something, it can't be sampled again. Now that means that we sample n the first time, but the next time when we're taking a ball out, there's only n minus 1 possibilities because one's disappeared. The denominator is changing all the time. And so when we multiply these up, we get n for the first one, n minus 1 possibility for second, down to n minus r plus 1. By the time we get to the end along here, the last one has only got n minus r plus 1 because we've taken away our events. Yeah, for the rth draw, we've taken away r minus 1 things already. So, so that's that, and that's given this notation npr, and it's equal to n factorial over n minus r factorial. And that's, you can think of as the total number of ways to take an ordered sample when you don't replace. In other words, they're all different. They're all got to be different. If n equals r, right down to the end, you just get n factorial, and that's just the total number of ways of putting n balls in n boxes, sort of total number of ways of assigning labels to people. It'd be if I assigned a random number, number 1 to 54 to each of you, the total number of ways you could be given numbers. Okay, so the classic example of this, which I want to do, is the birthday problem. Now this is, have people done the birthday? How many of us in the room? There's 4, 5, 5, 5. Oh yes, oh excellent. Oh, this is wonderful. I'm going to do a gamble here. I'm going to take a gamble. Okay, the birthday problem says, how many people do you need to have people matching a matched birthday? Okay, I'm going to take a little gamble here, and let's do a little test. Okay, I'm going to divide the room into 3, that bit, and that bit. And in this bit, there's 1, 2, 3, 4, there's about 23 people or so in each of these branches. Now, I bet that in at least one of these groups, 2 of you share a birthday. Do you think you do? Do you think any shared birthdays? Do you know of any? Do you know if any of you got the same birthday? I bet, it's not certain. I mean, in this room, I know there'll be a few people with the same birthday. It's bound to happen. So let's just do a quick little experiment. If you shout your birthday out, and if you're in this block with the same birthday, can you put your hand up? Okay, birthday.
24th August.
24th of August. Actually, if you've got it in the same room, also, if you hear your birthday, say it. But I'm really interested in the same block. 24th of August, yes?
December 1.
December the 1st? 7th of December? 21st of August? 10th of February? No matches yet? 16th of February? Oh, your birthday. Yeah. Jeffrey, your birthday. 8th of June. 8th of June? 17th of June? There must be some matches, come on. I don't believe you all got, yes? 11th of January. Yeah, you're 11th of January, okay. Yeah, okay, that's the first one. That's the first one. Let's find some more. Sir, your birthday, give him a shove.
Oh, yeah, 4th of December.
4th of December. 19th of February? April, 19th of April. 17th of November? December 24th? December 27th? God, there must be some more matches, I'm sure. Yeah? 8th of March? 14th of June. 14th of June? 29th of August? August 12th? Yeah, okay, one there. Right, good. And 6th, sorry? 6th. 6th of December? 1st of July? September 19th. September 19th. And yours? 14th December. So all of you had different birthdays. Oh, that's a bit disappointing. Okay, let's try this block. Yes.
March 27th.
March the 7th? 27th. Yep.
14th September.
14th September? 23 January?
10 May.
10th of May?
1st October.
1st of October?
1st January.
1st of January? Come on. Sorry, 1st of January over there. Okay, yeah, yeah.
12th of March.
12th of March. Yeah, 12th of March. 23 of December. 16th of May. 12th of August. We had a 12th of August over there, yeah. Okay, yep. 4th of January. 22nd June. July, was it? July. 22nd July. 29th of April. 28th of August. 23 of August, right? 28th of May. February 27th. 8th November. 24th of November. 30th of August. Right. Yeah. Alex. 10th of October. I failed on that one as well. This is dismal. This is terrible. No, I got to win on this one. Your birthday. 2nd of July. 12th of February. 11th March. 8th of July. 15th of May. What's yours? Hey! Yes. Thank you, thank you, thank you. Yeah. I thought probability was going to let me down. Terrible. Yeah, there was one in this block. 2 people with the same birthday. Cool, thank goodness for that. That would have been really unlucky. Yeah, okay. Sorry, and so 15th?
24th of May.
24th of May?
17th of August.
17th of August?
29th August.
29th August? April 25th? 13th of June? 7th September? 4th of November? Sorry? 6th of April? 2 matches. Whoa. This is a very special group. These are really, they obviously have strong connections. They're all born on the same day. Yeah. So, 21st of May? 31st of May, yeah. Sorry? Oh, no, we had that, yeah, yeah. And we've had yours. We know yours. 1st of January. 1st of January. We had one of those. Yes, yeah, exactly. Yes, I remember that. Yeah, yeah. April? 10th, yeah. 30th of September. Okay, that's good. Thank you very much indeed. All right. Now, why did I think that one of your blocks should have the same birthday? You just do the calculations. Now, there's different ways of doing the calculations. What I like, if you think of the calculations, what we're doing, if we line up all these people in a row, so this is all of you in a row, lined up, bum. And then the first one can have any birthday at all. So what I'm going to do is just like for the dice, I'm going to calculate the probability of no matches. That's the easiest one to calculate. And the probability of no matches, it means that, again, we're turning it into a series of ands. The first one can be anything. The first birthday can be anything. But the second one must be different from the first. So it's the probability that the second does not equal the first, times the probability that the third does not equal the first or the second, etc. So it's quite nice because the probability that the second doesn't equal the first, there's 365 birthdays, and there's in a way 364 remaining choices to have. So there's 364 left. Now the third mustn't, so now 2 have been taken. If we think of these birthdays 1 to 365, we've lost 2 of them, but the third person in the queue now has 300, to be different, is 363 of 365. Times blah, 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 and this goes down. Now each of these numbers is quite big, but when we multiply them all together, we end up with quite a small number. And it turns out that you only need 23 of these to get a number that's the probability of no matches is less than, I think 0.48, is less than a half. So the probability of a match is greater than a half. So it's quite a remarkable thing that you only need 23 people to get these coincidences. Now, I did it this way. Actually, I did it this way, which is the sequential way of doing it. So that's, I think, the natural intuitive way to think of it. To think of everybody in a queue and doing the calculations like taking socks out of a drawer. But we could do it a more formal way, which is to use our idea of a probability being a ratio of the number of ways obeying the property compared with the total number of ways. So if I want the probability of them being all different, I could calculate the number of ways of choosing birthdays that are all different, which is just NPR, because it's the number of, it's like sampling without replacement, divided by the total number of ways of choosing birthdays, which is like sampling with replacement. In other words, these people can have any birthday they want. In this situation, if I want them to be all different, it's like sampling with replacement. And when I put those in, that's the formula for the numerator, the formula for the denominator. I get out this formula. Now, so either way is correct. I find it's easier to go straight for the answer in a way, to go directly to that. But this is more, in a way, technically correct way to do it. Okay, so birthday coincidences is quite useful. Now, then we get into combinations. We're leading up to the binomial distribution for this thing. Because now we've so far been considered with ordered sets. Where you are in the row makes a difference. But what happens if we just want unordered sets? We just want the number of ways in this room of picking a group of 6 people, for example. So it's 55 people or something. If I needed to pick a group of 6, how many different groups of 6 are there? Now, the point is I could pick you out one at a time and work out, if I was going to pick you out one at a time and I'm labeling you 1, 2, 3, 4, 5, 6, then the total number of ways would be NPR, n factorial over n minus r factorial. But those labels could be assigned in r factorial different ways. So, because I'm not interested in the labels, I'm just interested in the number of groups. So I could pick you out 1, 2, 3, 4, 5, 6, say, but it wouldn't make any difference if it was 1, 3, 2, 6, 4, 5. You know, any one of these combinations would actually end up with exactly the same numbers, same people, if you were labeled with these labels. So actually, what we want to do is divide that by r factorial, and we get this. That's wrong. Now, come on, you've got to spot my mistakes and tell me my mistakes. That should have an r factorial in the bottom. Yeah, sorry, okay. That's r factorial. So that's wrong. So my example, yesterday, I didn't actually buy one. South African lotto ticket. South African lottery, which I didn't buy. I must buy a ticket. I should have bought. I'm too mean. I mean, why am I too mean? The point about that, South African lottery, you've got 49 numbers, so n equals 49, and you choose 6 of them. You pay, how much is it to join? Is it 10 rand? 10 rand. Okay. So you pay your 10 rand and you get r equals, and you choose 6 numbers. And if all 6 numbers come up, you get the jackpot. Okay, how many different unique tickets are there? Well, you've got 49 and you're choosing 6. So there's that many different unique tickets to buy, which is quite a lot. Anybody know how many it is? Do you know? Do you know? Anyone know? Guess? Quite a lot. Anyway, it's because it's 49 factorial divided by 6 factorial, 43 factorial, which is 49 times 48 times 47 times 46 times 45 times 44 divided by 6 times 5 times 4 times 3 times 2 times 1, which is equal to, come on. Honestly, you're so slow. It's equal to, actually I can't remember, it's about 13. Did you know this or have you calculated it? Or did you do it in your head? So what is it, 13? 93816, yeah. So there's nearly 14 million possible tickets. So the chance of winning the jackpot is 1 in 14 million. So that's why I didn't spend my 10 rand on yeah, 1 in 14 million chance of winning, yeah. Okay. But there is another way of calculating this. This is the, in a way, formal way to calculate. I think if I was going to calculate this again, I would say, there are 6 winning tickets, and I'm choosing 6 numbers. The probability that my first number is a winner, there is 6 over 49. So if I now think of picking my numbers one at a time, there are 6, in these 49, there are 6 winning numbers. It's like I'm reaching into a bag, and there are 6 pink balls and 43 black ones, and I've got to pick just the pink ones. It's the same problem. Turned into that problem, it's like socks in a drawer again. Now there's 49 socks in this drawer, 6 of them are white. I have to pick out all the white socks. Yeah. So the probability of the first one is 6 over 49. Now what's the probability that the next one is a white sock? Yeah, it's 5 over 48. There's 48 left and only 5 winners there. And the probability of the third one is 4 over 47 times 3 over 46 times 2 over 44. And then finally, there's 43 socks in, and only one of them is white. That has to be the right one. And when I do that, I get 1 over 13,980,000, blah, 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 blah. Now, that, to me, is a way more intuitive way to do the calculation. But the other one is quite correct. This one's quite correct. They're both correct. That's more intuitive. So you can see that all these problems, there are usually 2 different ways to do the calculations. So the message is, don't bother buying a lottery ticket. I think that's what, if we've learned one thing today, then don't bother buying a lottery ticket. Okay, I'm just going to finish off the last bit, just up to 12 o'clock, doing some slightly more technical things, which are not actually, for this course, I don't think they're very important. It's just I put them in case people want to go on and do more things in probability. These are the more formal ways to approach things. The important thing is to get to this, which I'm just going to get to at the end. We'll be working on these tomorrow, these distributions. Now we're getting onto the cool stuff. Real distributions for real quantities in the real world that we're going to be doing using in our statistical work. So, but some of this formal stuff is quite useful. So we're going to be a bit mathematical now for a bit. For an experiment epsilon, we've already done this. A sample space omega, possible outcomes little omega. And we're assuming that there's some probability law choosing some outcome from this space. We've got all these things that can happen, and something. So we've got all these are the possibilities, omega, and there's a little point in here, and nature somehow comes along and chooses this one, the observed one, according to some probability distribution. Now, if this is some subset A, we say the probability A is the probability that this omega has been chosen. So we're assuming that the probability somehow exists. And if we assume this probability, it means the probability that A will occur for a future experiment. Now, the point about this is that we want to define then a probability distribution on this space, omega, and we want various, the probability to have various properties. Now, to do that, it turns out that what we want to be able to do is define a probability distribution on a set of subsets of omega. And that set of subsets should obey certain properties. That's what's called a sigma field or a sigma algebra. Basically, it's quite straightforward. It says that if you've got some subset that is in the set of subsets you're interested in, then the complement's also in there. But this is the other thing, that if you've got a sequence of subsets, then the union of them is in there and the intersection are in there as well. So that if I've got a sequence of subsets, if I've got subsets around here, then all these, the intersection must be in my set of subsets that I'm going to define a probability measure on. So there's some restriction. Now, this is not important with these discrete spaces, but when you start getting into continuous distributions, it means there's certain elements, maybe some subsets, you can't assign probabilities to, according to this definition. Okay, so this is the really formal bit, which I don't want to get into particularly. It really just says these are sort of basic axioms of probability, defined in a more formal way, because a probability measure is defined on a sigma field of subsets, curly A, of a set omega, of a space omega. It's a real valued function, and we've done all this before, really. It just says that the probability over the whole space is 1. Each subset has got a non-negative probability. And if you've got mutually disjoint sets in A, so if you've got subsets which are non-intersecting, and you can have a countably infinite number of these, you've got to be able to count them, but you can have an infinite number, then there's the probability on all of these jointly is just the sum of the probabilities. So this is the addition rule, but applied now to infinite sets. Well, in a way, no, because the probability could be 0, yes. Yes, you're allowed to have sets of probability 0. For example, the empty set is in A and curly A and has probability 0. So you could have probability 0, but it is defined to be 0. So the probability is defined as being, so it's not like the probability doesn't exist in some sense. The probability is defined. And you can have sets of probability 0 within your set of subsets. Because certain intersections might be impossible. Yeah. So it's essentially is the empty set is included. So the probability space then is the overall sample space, the set of subsets in which the probability is defined, and a probability that's defined on these subsets. So what we're not going into, this all starts getting into ideas of measure theory, which is to do with general functions on sigma fields that extends well beyond probability into the whole idea of integration, Lebesgue integration, etc. And we're not doing that, thank goodness. So. But if you want to get deeper into probability theory, all these ideas start becoming important. They won't be relevant to what we're doing in our situations. So in a simple situation, discrete spaces, we can write out the set of all space of all possible outcomes. We can find curly A as a set of all subsets, including the empty set, and then the individual elements have got a probability defined as 0.25 for each omega I, and we can work out then from that, and the addition rule, the probability of all and of any outcome we want. So that's just the final bit in our sort of more formal approach, is we're going to define probability, conditional probability a bit more formally now. We've already looked at this, we've already sort of derived it intuitively, but more formally it's defined as a definition. The probability of B given A, when A has a non-zero probability, is the probability of B and A divided by the probability of A. And we're going to be using this a lot. The interesting thing, of course, is if P of A equals 0, this is undefined. Pointless to condition on an impossible event. So I thought of something. I thought, well, okay, here's something. If I turned into a bird, what is the probability I would be an eagle? Now, that is not a meaningful probability. That is a conditional probability, but it's stupid because the conditioning event A has got probability 0, I hope. So that's it. So if A is 0, this doesn't have a value. It's a pointless thing to even think about. So it's very important. So again, these events of probability 0 are really important because it's pointless to condition on them. So from these rules, actually all else follows. The complement rule can follow. The idea of the addition rule for intersecting sets follows. It's basically everything follows from those basic rules. If we've got two sets A and B that intersect, and that's sort of A intersection B, then the probability of both of those of A union B is the probability of that plus the probability of that minus the probability of that. So essentially it obeys, probability then obeys all the set theoretic constructs. Okay, now we're getting into the stuff that's getting more important, I think. It's to do with random variables, which are essentially numbers defined using a probability measure. The probability measure is we need that, But the crucial thing is the random variables, which is now defined as a function. We often think of a random variable x just a number, but actually mathematically it's defined as a function, because it's a function from the space of possible events to the real number r. So the real valued function is defined on a discrete, we're looking at discrete values, density functions at the moment. It's just the probability that x takes on some little value x. That's it. So it's pretty straightforward. And the probability that x is less or equal to x, remember x is defined on the real line, so we can define this, is called a discrete distribution function. The event x less or equal to x is interpreted as the set of events such that this function is less or equal to x. So essentially, we're defining something that goes from omega, and this, if we think of the random variable, is in fact a function, a mapping from there onto the real line. So it takes a probability space and maps it onto the real line R, onto some number. So for example, flipping a coin twice, we define a number, which is x as the total number of heads. So we're turning our most general probability space into a number, which then we want to do things like we want to put a distributions on. We do everything then onto the real line, and then we can start playing with these things, and it forms the foundation for statistical methods. So, for example, flipping a coin twice, the chance of the total number of heads, we can then say the probability of getting 0 heads, the probability of tail is 0.25, and then we've instantly now got a probability density function on these values. We've got a probability density, the values it can take on 0, 1, and 2, and we've got a lump of 0.25 there, of half there, and half there. So this is f of x for x equals 0, 1, 2, when this is the total number of heads when you flip a coin twice. Okay, so, and on these probability distributions, for discrete values, we can define various things. When we've got a distribution like this, we're interested in two basic things. The middle, where it is and how spread out it is. And we'll come on to more, but the natural summaries for these is the average of this distribution and the variability in this distribution, defined in these terms as the mean and the variance. This is defined for a finite set of possible values. The mean is just the average weighted by the probability of each occurring. So the average here would just be 0.25 times 0 plus 0.5 times 1 plus 0.25 times 2, and when we do all that calculation, we get 1. So this is expectation of the random variable here. These are the probabilities, these are the values it can take on, and we end up with something telling us the mean is 1, which we could have seen just by looking at the thing, but never mind. And the variance then is the average of the squared distances between the values and the expectation, averaged with respect to their probability. And we'll be doing all sorts of things playing with these. I won't prove it now, might get you to do it, but this is the sum of the squares of the xi's around the mean. You can rearrange this into a much simpler form and find out that the variance can be expressed as the expectation of the square of x minus the expectation of x all squared. There should have some brackets around it maybe. Okay, so these things I'm sure are actually going through this quite fast because I think this will be revision for most people who have seen these measures before, but they are important. Okay, so in the last 5, I'm going to do 3 minutes more, because I'm going to go fast through these things. They're on there. We're going to come back to these tomorrow, but I just wanted to get these distributions out of the way, and we'll come back to them tomorrow. Now we're going to do the proper stuff. Distributions. I love distributions. I'm afraid you're going to get bored silly by Poisson distributions and binomials and Bernoulli's. I just love it because it's the connection really between probability and statistics is distributions, because in the real world we observe numbers, we count things, and the connection is to say, well, we act as if they came from a probability distribution. And the simplest thing to count is whether something's happened or not. So it just takes on the value 0 or 1. And a Bernoulli random variable is just whether something happens or not, and it's given a probability p of it happening and 1 minus p of it not happening. That is the simplest random quantity, known as a Bernoulli trial. So every time I flip a coin, it's a Bernoulli trial with probability 1/2. When I throw a dice, it's a Bernoulli trial. Actually, I don't know if you've seen these. I got some really strange dice here. There's one with 8 and 10 sides, one with 12 sides. Nice symmetric dice. So when I throw this 12-sided dice, then that's and I'm looking for the probability of 1 coming up. It's a Bernoulli trial with probability of 12. So, and this, with these bones, if I'm interested in a particular side, this is a Bernoulli trial, and I've no idea what the probability is. Because it's got no symmetries. I have no idea. People have thrown these thousands of times. And they've actually done, they're just doing this and doing this thousands of times, trying to work out, can you imagine it? You can do a PhD on that. Actually, I might get you to throw these thousands of times and counted how many times. And they're definitely, there's one side, I think, which has got about a 60% chance of coming up, and others, it's unlikely they'll land on their edges and things like that. So those are Bernoulli trials, but if you're only interested in one edge, but we don't know what the probability is. Okay, and that's got expectation, just p, just the expected value for this, the average of these numbers, p times 1 plus 1 minus p times 0 is just p, and the variance is p times 1 minus p. And check my working, I hope it's right. Expectation, the square minus the square of the expectation, that's the square times the probability, plus p times 1 squared minus p squared, and that's 0, and when I take it out of the bracket, get p times 1 minus p. So the variance of a coin flip is just p times 1 minus p. Okay. Actually, I'm going to stop on this one. I only need to get to this one for today. Final thing, the binomial distribution. We've taken a long time together, but this is another mistake. I got there first. No, I made 2 mistakes on this one. That should be an x, and I've forgotten the x factorial there again. Yeah, thank you. I got there. That's just a race to spot the mistakes first. Okay, this is if you're the sum of n Bernoulli trials. So how many successes? If I throw this, I mark a side, I'm going to mark one side, and I throw this 20 times, how many will it, it's always that side. How many will it come up that side, one particular side? And that is a binomial distribution. It's the sum of n Bernoulli trials. Now, the crucial bit of maths here, it says that if I looked at a particular sequence, let's just do, I don't know, let's call this a head and a tail. So if I did 10 throws, and I could then get head, head, tail, tail, head, head, tail, tail, 1, 2, yes, a pretty unlikely set, but let's do that. Yeah, head, head, tail, tail, head, head. If I got that, I'd think I was cheating, but never mind. That's a particular sequence which ends up with 6 heads. So x equals 6. Oops. Now, the probability of that happening, if the probability of a head equals the probability that x equals 0, x equals 1 is p, would be p times 1 minus p times 1 minus p times up to p, and it would actually be equal to p to the 6th times 1 minus p to the 4th. Yeah. So that would be the probability of that particular sequence. But I'm not interested in that particular sequence. I'm interested in any sequence that ends up with 6 out of 10. So what I want to do is work out the probability of any of these sequences. So that's the probability of any specific sequence. Then I just need to know how many sequences there are. And we've done that. We've just done that, and we know it's n choose x, which is n factorial over n minus factorial times x factorial. So the basic density says that it's this times that value. That can be shown which I might get you to show, to have this mean and this variance, and so this standard deviation, which is the square root of the mean. Now the binomial, I've finished there because it's so important. It's the distribution of proportions. You know, if I do something n times, I observe r out of n. It's the distribution that tells us how proportions are governed. And we will use that again and again in statistical analysis. Okay, so I squeezed rather a lot in there. We're going to have a pause and then go upstairs. Now, I've done a much shorter practical, because there's too much yesterday. And it involves, though, using some of the, adapting some of the code from yesterday. But I hope it will be accessible. Are there any questions before we have a short break? Sorry, I've raced through it as usual. Sorry. Has anybody got any questions? I haven't given you much of a chance, I'm afraid. Okay, so what I'm going to do is I'll be around. Please come and talk to me. And we should have a short break now and go upstairs. And is that okay, Emma? And ready to go. And make sure you run the code for the dice and sort of understand it. Actually, the double 6 one is quite, I'm not sure if I understood that. But, but the other ones is fairly straightforward. And so have a go at using the code and the next problem. And also work together. You're working really well together yesterday in groups, small groups. That's just fine. Works very well. Please do that. And please ask us about any problems. Okay, thanks very much.